Hey y'all, it's me, Mr. Crone. I hope that you've been enjoying these lessons and that you're able to do your work. Remember to reach out to your teachers if you have any questions. Today we're going to talk about motion and force. So I need you to log into Nearpod. Our code today, today is AMDRJ. Again, it's AMDRJ. You'll hit the arrow. Put your name, your homeroom. Still have to reload mine. Still not quite sure why, but I'm out here today, just in my front yard. It's kind of nice. Alright, so in this lesson, students will be able to understand what a force is, understand the difference between balanced and unbalanced forces, and be able to calculate net force. So by the end of the day, you'll be able to tell what a force is, know how to tell the difference between a balanced and unbalanced, and to be able to calculate net force. Starting off, open-ended question. What is a force? So for you that are going to do it on your own, you'll type in the box, what is a force? I need you to think about, force. I remember from class that a force, is a push or pull that changes the motion of an object. Complete sentence. A force is a push or pull that changes the motion of the object. Once I'm done, what is a force? A force is a push or pull on an object. So you see these two little dudes. We got one guy pushing, we got another person pulling. Those are both forces. In the following video, you're going to understand there are forces everywhere on Earth. If you got headphones, put them in now. We'll watch it together.
Do you know where the forces are in the world around us?
Looks fun.
The world is full of movement. People pushing and pulling. The wind blowing in the trees. People on their bikes. None of this would happen without forces. Forces can be strong enough to launch a rocket into space, or make buildings fall down during an earthquake. The forces we're likely to see and feel every day are less dramatic.
I see a push.
Sometimes we can't even see them, but they're still there.
What's working on that ball? I wonder. Why did it stop? So I want you to think of some of the forces that you saw in the video. And I want you to answer this question. What are some forces that are acting on you right now that you can't see? So wherever you are, there's some forces acting on you. What are they? For me, the forces acting on me right now, let me think. Well, I'm not floating off in space, so something's holding me down to Earth, pulling me towards the center. Oh yeah, gravity. But I'm not sinking to the center of the Earth. Something's holding me up. What could that be? Oh, my chair. My chair's pushing me up. The particles are holding me up. What else? Well, I'm not sliding all over the place, so there must be some friction. Is holding me in place. And you might have been able to think of some more. So again, submit it. How are forces measured? Excuse me. how are forces measured? They are measured in a unit called newtons. We use an N for newtons. You might remember that from before. So we use newtons because the guy that kind of was the person that kind of started thinking about this, making all these interesting observations, was the guy named Isaac Newton. To make this car move, the person pushes with a force of 500 newtons. So the force is pushing, and we measure the force in newtons. That's 5,000 of them to make it move. That's a lot of newtons. If you look down here, you can see an arrow that shows both the magnitude, that just means how strong the push is, and the direction that the force is applied to the car. So this lady's 5,000 newtons going towards the right. So the arrow will show the strength and the direction of the force. This person is pushing the box with a force of 450 newtons. Label the picture to show the direction and strength of the force. Well, the push, that means it's going to go towards the right, and 450 newtons will be the strength. So I'm going to come over here. I'm going to use green because it's my favorite color. I'm going to push, the direction is towards the right, and my strength is 450, excuse my handwriting, newtons. So the force is 450 newtons towards the right. Once I think I got it, I'm going to hit submit. There we go. Looking at this picture, person A pulls with a force of 500 newtons, and person B pulls with a force of 100 newtons in the opposite direction. So this person's pulling to the left at 500 newtons, person B is pulling to the right at 100 newtons. So you can see the arrows are different sizes because the forces are different sizes. And the directions are different because the force is going in different directions. Whoops, I just kind of went over that. Person A's is longer than person B's because the forces are different. Alright, so let's label this diagram. The person on the left, this person right here, is pulling with a force of 450 newtons, and the person on the right is pulling with a force of 200 newtons. So, first thing I think of is, well, the forces are different, so the arrows can't be the same length. So the person on the left is going to have a longer arrow, so I'll draw her arrow now. And she's pulling the rope towards her, so it's going to be going to the left. A little longer. 450 newtons. And the person to the right is, I'll change her color to orange, is pulling to the right with a force of 200 newtons. So again, the forces are different, so the arrows have to be different lengths. They're also going in different directions, so their arrows are pointing in different directions. When you're finished, you'll hit submit. So what are balanced and unbalanced forces? Well, balanced forces are equal in strength. They don't change an object's motion. So if the arrows were the exact same strength, the exact same length, they'd be balanced. Unbalanced forces are not equal. So that's like the last picture. The two forces were not the same, and they're going in opposite directions, so that's going to cause an object to change its motion right here. Remember, if it's staying the same, it's balanced. If it's moving, either getting faster or slowing down, we say it's unbalanced. Are these forces balanced or unbalanced? Let's look. So this teacher is pushing with a force of 450 newtons, and this one's pushing at a force of 250 newtons. They're going in opposite directions, but one force is way bigger, so this table is going to be in motion towards the right. So we're going to say they're unbalanced. I hope that's what you would say too. So forces are balanced on both sides. There is no change in motion between these two teams. So you can see this team is going 400 to the left. This team is going 400 to the right. Because then forces are the same, they cancel each other out. The net force is 0. This rope will not move. We say it's balanced. But over here, because some of these people are stronger, these forces are unbalanced because the team on the left is pulling with more force than the team on the right. So the rope is going to move towards the left team. Since the rope is moving, we say the forces are unbalanced. It's true. I want you to find a partner. We can't do it in our classroom, so you're going to have to do it with a brother and sister. Find a chair or something that you can push and try this out. So the first time you should be both pushing the desk to making sure it doesn't move in either directions. Explain why it doesn't move. So you and your brother and sister try to be pushing against something but make it so it doesn't move. And then the second time, plan that one person pushes with more force than the other person. What happens to the desk? So the first try, push so that the desk doesn't move. Second try, push so the desk does move. When you're finished, come back to the video. So what happened for number 1? Why didn't the desk move even though both are pushing on it? So I would say in test number 1, the desk did not move because, let me think. Well, if both people were pushing on it but it wasn't moving, the forces must be the same or balanced. So I would say because the two forces acting on the desk were balanced. So then what about test 2? Why did it move? So in test number 2, the desk did move because the forces were unbalanced. One person's force is greater than the other, which means they didn't cancel each other out. The desk moves. When you're finished, you'll submit. So when you're calculating the net force, it's actually pretty simple. We've talked about this before. You subtract the smaller force from the larger force. So in this example, 500 and 100, you take the larger force, you take away or subtract the smaller force, and your total force is 400 newtons towards the left. So the forces, since they're going opposite directions, cancel each other out. But since this one is 400 bigger, the force is going to the left. We're going to practice this. Net force answers the strength of how many newtons in an arrow showing the direction of the movement. So when you're telling the net force, you need to tell the strength and the direction. So if you just wrote 400 newtons, you'd be wrong because it wouldn't tell me what direction. So you need to be able to tell me which strength and which direction. When two forces act in the same direction, they're working together. That means you add them together. So in this example, this person is pushing right here, and this person is pulling right here, and they're both moving the box in the same direction to the right. Since they're working together, the forces are added together. So 600 newtons plus 75 newtons. The total is 675 newtons to the right. You'll also notice that the arrow got longer because you're adding the two forces together. So just like before, you need to tell me the strength and direction of the force. So in the next slide, open the net force activity. And then you need to add people to both sides of the tug-of-war rope to see how the net force will change. This is kind of cool. Alright. So we've got a cart full of Fruity Pebbles, maybe? Lucky Charms, I'm not sure. And we're going to put together some teams. Well, we know we want some strong people on our team, so I'll put one on this side and one on this side. These people look about the same. Watch what happens when I push go. they're both pulling with the same force in opposite directions, that means we're subtracting. So 150 minus 150 is 0 newtons. So the thing is not moving. But watch what happens when I add another person to this blue team. All of a sudden, the force is bigger on this side. The cart goes in motion, and our total force is 50 newtons to the left. Oh no, stop. Oh, too bad. Alright, so look what happens. I've added more force on this side. Now it's 250 to the right and 200 to the left. Subtract the smaller number from the bigger number. The total force is 50 newtons to the right. They pull. Play around with it. As you see, when I took away this guy, the force is 0. It's going to stay the same motion until something changes. We're going to talk about more of that in our next video. Cool. So play around with that. See if you can find more ways to make balanced and unbalanced forces. Alright, the quiz at the end. What is a force? A push, a pull, both push or pull. Well, hopefully you'll be able to answer this with no problem. Both push and pulls. Question 2. What is the main difference between balanced and unbalanced forces? So balanced forces cause a change in an object's motion. So if forces are balanced, something's going to change its motion. Is that true? Unbalanced forces can cause a change in an object's motion. Well, that's true. But let's see if there's another answer better. Balanced forces are unequal in strength. So their forces are not equal. Unbalanced forces are equal in strength. That's not true. So both of those are wrong. So our best answer is B. Way to talk it through, Mr. Crone. So in this diagram, what is the net force? So I see that we have 500 newtons to the left and 100 newtons to the right. I remember calculating net force that are different. You subtract the smaller from larger. 500 newtons take away 100 newtons is 400 newtons, and our direction is to the left. So 400 newtons to the left. Okay, that looks perfect. 4 newtons to the left. Next. If two forces are acting in the same direction, how do you calculate the net force? So if the two forces are working together, what do? Do you subtract the smaller force from the larger force, add the forces together, subtract the larger force from the smaller force? Well, if they're working together, you're not taking anything away, so both the subtracts can't be right. So it's got to be B, add the forces together. Last one. Looking in this picture, a boy is trying to pull a dog on the leash, but the dog and the boy are accelerating in the same direction to the right. Which of the following best describes the forces in this simulation? So let's look at the picture. This boy is trying to pull the dog to the left, but the dog is pulling him to the right, and the movement is to the right. So what's happening to the forces? Are they balanced, unbalanced? What directions are they moving? Let's go back to our answers. The forces are balanced, the net force is 0. So if the net force is 0, they won't be moving. But look at our picture, it says they're moving to the right. So that can't be correct. The forces are unbalanced. The boy is pulling with a greater force than the dog. So it says the forces are unbalanced, but the boy is pulling the dog towards him. That's not true, because the boy is pulling to the left and they're moving to the right. So it can't be B. The forces are unbalanced. The dog's force is greater than the boy's. So it seems like that could be true because they are moving the way the dog's force is going. But let's just make sure that this one makes the most sense. The forces are balanced. The dog is pulling with a force greater than the boy's. Well, obviously they're not balanced because the dog's force is greater than the boy's. So that would say they're not balanced. So our best answer, the forces are unbalanced. The dog's force is greater than the boy's force. I would choose that. Let's see how I did. Hooray, 100%. That's what I like to see. Good job, Mr. Crone. Alright, moving on. Here's some different things you can click on to learn more about this topic. You're welcome to do this lesson as many times as you want, practicing your calculating different forces and directions. If you've got any questions, let me know. Thanks. Bye.